And so we've got A gamma acts on the Deligne complex, which is a nice two-dimensional cat zero simplicial complex. And we said, so the action is co-compact. It's turns out it's also an action without inversion. What's also going to be very useful for us is that, so why do we care about actions on anything, really? We're generally trying to kind of decompose our group into kind of smaller blocks, smaller pieces, namely the stabilizers of the simplices and all that. And these building blocks are arranged using the combinatorics or the geometry of the underlying complex. So we are hoping that the building pieces are simple enough, well, not simple in the algebraic sense, easy enough to understand so that we can hope to leverage that into some information about the whole group. So here the stabilizers are exactly, by construction, they are the parabolic subgroups of spherical type. And so in particular, there are of three types, type 0, type 1, type 2. And so we get stabilizers that are either trivial, infinite cyclic, or what we call like dihedral Artin groups. And what we'll see a bit later is that these ones are actually virtually Z cross free. So they're nice. They're very nice. So we've got nice enough building blocks and a nice geometry. And now we can try to use that to prove stuff. So what do we want to prove? We wanted to prove the Tits alternative. So we want to understand the subgroups of A gamma and prove that they're either very big or very small. And very big means they contain a copy of a non-abelian free group. So today we're going to focus mostly on how to construct free subgroups. And in geometric group theory, constructing free subgroups is something we really like. So what is the ideal scenario when you're trying to construct free subgroup of a group? When you have a group acting on something, what is kind of the ideal setting so that we can guarantee that you're going to be able to construct lots of free subgroups? Ping pong. Ping pong is like the go-to method to construct free subgroups. And what is a nice sort of geometry that allows you to play ping pong? Hyperbolic geometry. You generally, it's kind of like how you prove the Tits alternative for hyperbolic groups is you play ping pong using the Gromov boundary. So the ideal scenario in an ideal world, this is what we would be doing. Spoiler alert: we do not live in an ideal world. G acting on a hyperbolic space. But just having a hyperbolic space is not enough. If you don't know anything about the action, you're going to struggle to actually construct free subgroups. So what is a nice kind of condition on an action that allows you to construct lots of free subgroups? And we've kind of hinted at, not in this mini course, but in another one. So yes, it's the notion of acylindricity. So if you have an acylindrical action on a hyperbolic space, then you can construct lots of free subgroups. So in Anne's course, we've seen the notion of a WPD element. So acylindricity is kind of WPD on steroids. So essentially every loxodromic element is WPD, and there's some sort of uniformness with the constants involved. So that's kind of, if we were, I guess, like a first naive attempt to construct lots of free subgroups as a first step towards the Tits alternative, is to try to put ourselves in this scenario, right? So two bad news. So I said, so we got two conditions. Two bad news are coming. So, so I said the only Artin group that matters is this one. In this mini course, so other people care about other Artin groups, but we're going to care mostly about this one. So even just for that one, d gamma is not hyperbolic. So I mentioned that the corresponding Coxeter group is the tiling of the Euclidean plane, and we're going to see copies of the Euclidean plane, lots of copies of the Euclidean plane. So kind of the Deligne complex is made of lots of these copies of the Euclidean plane. If you're wondering, lots of copies of Euclidean plane together, ooh, do we have a building? No, and I'll mention that in a bit. So it's the Deligne complex is made of lots of copies of the Euclidean plane, but the arrangement is a bit wilder than in the case of an affine building. That's the first bad news, and the second bad news is that the action is not acylindrical at all. We're doubly, I mean, we're angry at this point. So we're not going to do that. Actually, there's one case. So I lied. This 333 is not the only case we're allowed to look at. If we do 444, then this one's become a smiley face. Then the Deligne complex becomes hyperbolic. However, the action is still not acylindrical. But with Piotr, we managed to kind of construct a deformation of the Deligne complex, or a conoff of the Deligne complex, to force the action to become acylindrical, and use that to prove the Tits alternative. So these sort of ideas, you can use them not like on the nose with the action on the Deligne complex to prove the Tits alternative for at least like extra large type Artin groups, right? So those Artin groups when there's a nice underlying hyperbolic geometry of the Deligne complex. But we are interested in that one, and here everything fails, so we're going to try to do something completely different. Right. So how else can we construct free subgroups? So maybe to get some well, okay, so maybe before what I want to say, so how are the elements acting on the Deligne complex? So you're probably familiar with the kind of Holy Trinity, loxodromic, parabolic, elliptic. So how can elements of the Artin group act on the Deligne complex? Actually, it's not too bad. So an element of A gamma is either, and I'm going to use the same convention I think as in Anne's course, when we talk about loxodromic, either loxodromic, and when I say loxodromic, is really for the action on the Deligne complex. So we're really focusing on this action now. So loxodromic, that was defined as the orbits are QI embedded. We're in the cat0 space, so there's an even like nicer way to think about loxodromic elements. So because of cat0ness, there exists an axis. So an embed, which is what we mean is really a convex line on which G acts by translation. That's the first case, so loxodromic. The second case is elliptic isometries. So elliptic is generally defined as, well, not generally, it's defined as having bounded orbits in our space. But bounded orbits, because again, we're in a cat0 setting, this, and cat0 complete, this means that G fixes a point in my space. That's a very powerful result about cat0 geometry. If you have an element that has bounded orbits, it actually fixes a point when you are in a complete cat0 metric space. And that's kind of, for instance, a key tool to try to understand the finite order elements in a space. And actually how you can prove, for instance, that those two-dimensional Artin groups are torsion-free using that sort of result. So it fixes a point, but the action is without inversion. So actually, if you fix a point, you actually fix the point-wise the minimal simplex that contains it. So actually, you can assume that G fixes a vertex of D gamma. And well, the last one is generally parabolic. And parabolic are the messy ones that everyone likes to avoid if possible. And we're lucky we can avoid them. The reason being that we are in a simplicial complex, so a piecewise Euclidean simplicial complex where we only have finitely many types of isometry types of simplices. Right? That's something we talked about in the recitation class. And when you have only finitely many isometry types of simplices, it's a result of Brightson that in that case an isometry can only be what's called semi-simple, either elliptic or loxodromic. So we're going to try to construct free subgroups, knowing that the elements in our group only act in that way, either elliptically or loxodromically. Right. So, for instance, it's probably something that you've seen for actions on trees. Yeah. Yeah.
Which part of it are they sort of see that it fails? Is it the uniformity or is it?
As it's infinite. I'm going to talk about them actually very soon. Actually, just the generators, the standard generators, so the ones corresponding to vertices, their fixed point sets are, for instance, in that case, are going to be infinite, unbounded. So it's not like a subtle lack of acylindricity. It's really it just doesn't work. So yeah. Other questions actually? So no, okay. So right. So I mentioned actions on trees. So let's maybe use that as a motivating example. So maybe you've seen that result. So lemma. So here's another way to construct a free subgroup in a tree. So we have G acting on a tree, simplicial tree, and you have two elements A and B that act elliptically, so they have fixed points. Such that their fixed point sets are disjoint. Okay, we're going to need a slightly, we're going to need an extra condition. I'm going to try to explain why we need it in a sec. And for all k non-zero, the stabilizers, the fixed point set don't get bigger if you take larger powers of your elements. It's kind of the simplest situation to deal with. It's just that maybe looks slightly less natural. And then I'm also going to assume that these elements have infinite order. So that's kind of the hypothesis, and the conclusion is then the subgroup generated by A and B is free. So here I don't have any condition on the kind of dynamics of the action, save for the fact that kind of condition here about how powers of A and B act. Right, and the proof is not very difficult. So it's essentially a picture. So let's draw that. So I've got the fixed point set of, well, I'm in a tree, so technically I should draw a little subtree. The fixed point set of A is here. The fixed point set of B is here. And so now I'm trying to prove that if I take any reduced word non-trivial in A and B, the element of the group that I'm getting is non-trivial. And the way I'm going to try to do that is I'm going to show that this element acts, kind of moves some point in my tree. And the way to do that, so let's consider a geodesic gamma between those fixed point sets, between fix of A and fix of B. They're disjoint, so I'm allowed to do that. So now let's try to understand what happens. For instance, if my word W that I'm trying to understand is just say A square, B square. I'm trying to prove that this element, this word defines a non-trivial element of G. So let's try to understand the effect of this element on gamma. So I'm going to do kind of syllable by syllable. So what happens if I first do a square applied to gamma? So what's going to happen is that I'm going to turn around this. So A fixes that yellow vertex here, so does a square. So when I do a square, I end up here. So I've really turned around around here, and the fact that these edges are distinct, so the concatenation doesn't backtrack, exactly coming from this reason here. If these two edges were the same, that would mean that a square would fix that edge here. So that would mean in particular that a square has a bigger fixed point set than a, which is ruled out by this condition. So that what I'm really seeing here is no backtracking. So that's a square b, and now so I've got here I've got a square fix b, and if I apply now b square to the right, I'm going to see something similar. I'm going to see a square b square gamma, and for the same reason here, there is no backtracking. So it means in particular that if I take the union of all these three geodesic segments, so it's something that lives in my tree and it's a non-backtracking path, so it's a geodesic. So in particular, it means that gamma is different from a square b square gamma. Okay, so this is a geodesic. And in particular, we see that gamma is different from, so the kind of initial segment is distinct from the terminal segment. And so in particular, that proves that a square b square is different from the identity. Okay, and now you can do that for any reduced word. You just have like more steps when you do the thing, but it's always the same argument that at each step of the process there's no backtracking. So what you're gonna see is really a geodesic embedded in your tree. Yeah.
I didn't understand what you meant by backtracking.
So backtracking is, when you have when you have a tree, you have two geodesics in your tree. There is backtracking if like the final edge of the first bit is the same as so kind of you go back. So you do this, and then you do that, and then something like this. There would be backtracking. Okay, and so in particular, you could not conclude that the union is a geodesic, and depending on how, if fix of a to the a square, a cube, a to the 4 get bigger and bigger, it becomes much more complicated to understand how these translates of gamma kind of behave. And
so there's no backtracking in the concatenation of gamma with a square gamma.
so yes, there's no backtracking between gamma and a square gamma. Okay, and that comes from this condition here, the fact that fix of a is the same as fix of a squared. Yeah, other questions?
Why does follow that this generates a free group then? Like, I understand that this is not a trivial element, but
so well, you do that for any. So I took a single example, a squared b squared, but you can do that for any reduced word in A and B, and the same argument shows you that, well, for the same procedure, gamma is going to be different from that word or the element corresponding to that word applied to gamma. So that element is non-trivial. So this means that any reduced and non-trivial element of in A and B defines a non-trivial element. So that precisely means that you have a free group on A and B. Yeah. Other quick.
How restrictive does this fix that condition? Like, does something weird happen if there is an element that has?
Sorry.
If there is an element whose like fixed set continues to grow, is that possible? Or is
it happens. So here's an example. For instance, just taking a product with amalgamation. So let's say xy with the condition that x squared is equal to y cubed. And well, we don't have time to look at that in the exercise sheet, but that's actually that's the dihedral group, dihedral Artin group A3. So two generators and ABA is equal to BAB. So, but in particular, you can think of that as if are you familiar with amalgamated products? Okay, so it's Z. So it's an amalgamation of two copies of Z, the one corresponding to X and the one corresponding to Y. So maybe I should write it like this. Amalgamated along another copy of Z, which corresponds to the identification between x squared and y cubed. And so in particular, if you look at the Bastard tree of that splitting, you're going to see, for instance, that the fixed point set of X is just the single vertex corresponding to that particular coset. But because X squared is equal to Y cubed, X squared is going to stabilize in particular that edge between X and Y. So in that case, it does get bigger. And so in particular, well, it's clear just from that X and Y do not generate a free subgroup.
And this is this Artin group, so it is something really.
It is something that can happen. However, it happens for that looking at the action on the Bastard tree. However, it will not happen for the action on the Lin complex. For the action on the Lin complex, the fixed point sets are always going to be like stable in that sense. So we've got a bit more control here. Other questions? So our goal is essentially to copy paste this into the world of cat0 spaces and the world of the Lin complexes. But actions on trees are extremely kind of rigid, and the geometry of trees is much nicer than the geometry of arbitrary cat0 spaces. So this does not work in general at all. So there are some things that work. So let's where am I? So maybe to give a bit of context, I'm just going to mention some kind of open questions in the general case. By the way, until when do I have Kasia?
20 more minutes.
20 more. Okay, so I'm going to briefly mention the context. So these questions of if you have two elliptic elements that have disjoint fixed point set, can you kind of create a free subgroup out of this? It's kind of related to some interesting questions. So questions. So if you have, say, a finitely generated group acting on, say, like a finite dimensional cat0 complex, right, so can G contain infinite torsion subgroups? The assumptions are probably not optimal, but
you want to assume that the action is proper.
you
want the trivial action.
Yes, I do need something. No, I want the action to be right. Can G contain infinite torsion subgroups acting non-trivially? So if you have a torsion group, so every element has finite order. So as we said before, because of the cat0 geometry, if you have a finite order element, it fixes a point. Okay, and the goal is, does that, if that's true for every element, does that force the existence of a common fixed point for absolutely every element? Right? In which case, that would be a trivial action. That's not very interesting to study our subgroup. Right, so it's an open problem in general. There's some recent results. So the answer is no for two-dimensional cat0 complexes. It's due to Norino Zaida and Przititsky. There's another kind of generalization of this, which is there? Okay, so maybe it's a different type of question. If every element of H has a fixed point, does H have a fixed point? Which is kind of the a kind of general version of this. So these kind of actions where everything has a fixed point are called locally elliptic actions. And there's a recent work of Tomatel and Damiano Zaida on this, where they prove that for certain classes of spaces, yes, the answer is yes. If you have a locally elliptic action, it forces the action to be globally elliptic. So there is a general fixed point. But this is open in general and for cat-zero spaces in general. But in particular, what's the typical thing that can happen if you have two of your elements A and B in H? So they are elliptic individually. And what happens if their fixed points are disjoint? So what you'd like to do out of this is to be able to show that, or to construct an element of infinite order. To show that you cannot be in the torsion case, for instance, and to just show that one of these, and to prove that it doesn't have a global fixed point, what you would like is to try to construct a loxodromic element, so an element that is not going to have a fixed point. So if A, B elliptic and fix A intersect fix B trivially, does the subgroup generated by AB contain a loxodromic element? That sort of result would kind of solve those two problems, because a loxodromic element has infinite order, so your group could not be torsion, and well, loxodromic element does not have a fixed point, so it would also do this, right? But this is a kind of, it's generally a hard question. In the case of the tree, the answer is yes, and you can use that to prove to construct lots of loxodromic elements. What we're going to do is to essentially show that everything works well in the case of the Artin group acting on its Deligne complex. So kind of the key propositions, so kind of the machine for constructing free subgroups. So A gamma is a two-dimensional Artin group acting on its Deligne complex D gamma. A and B in A gamma are elliptic. And we know that A gamma is torsion free for different reasons. So these elements are infinite order as before, and have disjoint fixed point sets. Yeah, it's equal to the empty set. Then there exists an integer n such that the subgroup generated by A to the n and B to the n is free. So in the case of the tree, just A and B was enough. In the case of a two-dimensional Artin group, it's not going to be true in general, and you can really see in some concrete examples that it's not true for n equals 1. And moreover, we completely understand the elements that are loxodromic. G in A to the n, B to the n is loxodromic if and only if G is not conjugated to a power of B to the n or B to the n. So those elements conjugated to a power of A to the n and B to the n, they are clearly elliptic, because A to the n itself and B to the n itself are elliptic, and taking conjugates does not change the type, elliptic or loxodromic, but this is essentially the only case where you have something that is not loxodromic. So you have lots of loxodromic elements, and you can construct lots of free subgroups. So it's this is really going to be one of the key tools to construct free subgroups and to prove the Tits alternative in Thursday's lecture. And the proof. So this is essentially going to be the same proof, but with more things to check. But the strategy is going to be essentially the same. So this time around, we're going to be in a two-dimensional complex, so that the fixed points are going to be kind of blobs and etc. So still convex, but not necessarily subtrees. But we're going to do the same construction of taking a geodesic between the fixed point set of A and the fixed point set of B, and then looking at the actions of the various powers of kind of the subwords of our element, and showing that we are going to get a geodesic. So what do we need? So that worked well in the case of a tree. Why do we need in the cat0 case in more generality for this to work? So what worked before, kind of the key thing was that here we have no backtracking. If we have no backtracking, that guarantees that the union of two geodesics is again a geodesic, right? So we need a replacement for that in the cat0 world, and thankfully we do have one, because being cat0 or being a geodesic in a cat0 space is a local condition. So let me mention this. In the cat0 world, we have, well, I guess something that we can call the concatenation lemma. So we've got X that is cat0, and, well, gamma 1 and gamma 2, two geodesics that meet at a point X. And what we are trying to understand is the union again a geodesic, which is exactly the thing that we want to for the thing to work. And we have that gamma 1 union gamma 2 is a geodesic if and only if they make an angle at least pi at X. The case that we're working with here, so you say, what does it mean to make an angle in an arbitrary cat0 space? Let's just, we are in the case of, say, a cat0 piecewise Euclidean complex. So we have, all the simplices have like a metric, and they are identified with a triangles. We are allowed to define, to measure angles using those kind of model triangles that live in the Euclidean plane. So essentially we're using, for instance, if X is a vertex, the angle is just the angular metric in the link between the points they define. Okay, so we have this local condition. So this strategy will work if we can show that for some large power, or possibly large power of A, gamma and A to the n gamma and all its powers make an angle at least pi. Okay. For some n at least, for some n at least one, yeah, gamma and A to the n gamma, and same for B, make an angle at least pi. Right. So how do we understand this angle? And that needs to be for any element A, not just like your favorite one where you think that you can understand the angles a bit better. So to understand the angles, we're actually going to use something that I hinted at in the recitation class when I talked about how to understand the links in the type 2, where the length of the loops were kind of related to the ways to write the elements as like products of powers of A and B. So before we do that, we need we need to understand the fixed point sets a bit, because we're going to be using that. So elliptic elements in A gamma are such that, so we have essentially two possibilities. So the fixed point set is a single vertex of type 2. So for instance, well, we'll see some examples in the exercise sheet for tomorrow, for Thursday. So that can happen, that the analytic element has a fixed point set, which is a single vertex. So it's kind of a nice situation. But also what can happen is a non-trivial, so a tree with at least one edge, so not a vertex. And that happens exactly if and only if G is conjugated to a power of a standard generator. So we've got, in particular, something maybe I'm going to mention now. If your graph gamma is connected, if it's not connected, your Artin group splits as a free product. So essentially, you can understand that a bit differently. If gamma is connected and has at least 3 vertices, there's always at least one such fixed point set that is unbounded. And in particular, this implies that the action is not acylindrical in that case. That these are really the fixed point sets that are a bit problematic. So in the Deligne complex, you're really going to see something. So these are called like standard trees because they're trees associated to those standard generators, but they're really going to be like convex and go in some cases at infinity. So in particular, you have the whole Z subgroup generated by A that fixes pointwise every point on that tree. So that's a clear violation of any like acylindricity. Okay, right. So I'm gonna focus mostly on no, it's too much. I'm gonna focus mostly on those ones because they're easier to deal with. But they're already going to give you a good idea of the sort of tools we need. So essentially, we have our element. So we called it A before. So let's use it. Let's call it A again. Fix of A is that single vertex, and I'm looking at a geodesic gamma. Don't really know where it ends in fix of B, but we don't care at the moment. And what we want to understand is what happens with A to the K gamma, etc. What is the angle between those two things? So let's look at this. Understand the angles is essentially understanding what happens in the link, right? If I kind of take the link here, I want to understand what's the distance in the link for the angular metric between those 2 points. Let's call them gamma bar and A to the K gamma bar. That's really what I have to understand. And for that, I need to kind of understand the angular metric. So let's, again, gamma is equal to 333. So it's the same picture as I did before. I had my main triangle, so my kind of fundamental domain for the action of the Deligne on the Deligne complex. And I've got, this is going to be fix of A. And I've got stuff in my link, which like say a path in my link corresponds to a path of triangle around V. So if I have like I call X well, actually it's not necessary. Let's see. If I have here my triangle, my fundamental domain K, here I have, for instance, A to the A square K. Here I've got A square, B square, K, etc. So the length, so the distance in the link, so for the angular metric between X and let's call that WK is the number of syllables of the word W. And what's a syllable? A syllable is a power of either A or B. So you're probably familiar with the word metric, where you really count the number of A's and B's and A inverse and B inverse that appear in your word. Here, we kind of group them together so that we have A to the 5 counts for only one syllable, B to the 3rd counts for only one syllable, etc. Yeah. So in particular, the key thing is that the distance in the link of V between a point X and G of X is up to a constant, what's called the syllabic length of G. So the minimal number of syllables when you write G as a product of powers of A's and B's. So now this reduces the question of measuring the angles into something a bit more combinatorial, understanding how to write elements of the dihedral Artin group in such a form. And thankfully, there's a very nice result of Nicolas Vespu, who essentially completely understood what happens if you take large powers of elements. So it's a result of Vespu. If you have, so this, if G is an element in your dihedral Artin group, then the syllabic length of G to the n grows linearly with n if and only if G is not conjugated to a power of A or B. And so that's something you can prove while using a bit of a mix of actions on trees and a bit of what's called Garside theory for dihedral Artin group. But that's exactly what we need here to guarantee that if we have an element whose fixed point set is a single vertex, which means in particular that that element is not conjugated to one of the two generators, then by that result, the syllabic length of its powers is going to explode, which means that at some point, the angle between gamma and G to the n gamma is going to be as big as you want. And so in particular, it's going to be bigger than pi, and you're going to be able in this way to carry out the same strategy. That's for these types of elements. The case where the fixed point set is a tree is much more technical. In particular, this approach cannot work. The angles are not going to explode, so you need to be a bit more careful. Right, so I'm going to stop here. Thank you.
So we'll continue with the presentation session for about 25 minutes. And before we go, well, okay, first are your questions. Sorry, I forgot about that one.
Well, everyone wants coffee. So
I also have a second problem sheet. So I'm going to just pass it. And if there are questions, that's good enough. If not, we can all get a copy. Right, also need a coffee.
yeah, everyone needs a coffee, so that's okay.
Yes, well, people have questions for the. Oh, we need to sort of review.
I guess yeah, we can do that. Yeah.